If you picture uranium, you probably imagine a glowing green rock shooting out deadly invisible rays. But uranium pulled straight from the Earth is actually a heavy, dull gray metal. Getting power out of this dense metal isn't as simple as tossing it into a furnace. To reach the massive energy hidden inside, we have to force the material through several radical physical changes. As the metal goes through these changes, the specific hazards it poses shift along with it. Understanding this element means moving past the pop culture cliches and tracking the material through three distinct phases. First is the dirt, second is the gas, and third is the weapon. The process starts in the dirt. Because uranium is spread incredibly thin throughout the Earth's crust, miners have to excavate staggering amounts of soil and rock just to find a tiny fraction of the usable material. Once the uranium is separated out, you're left with millions of tons of waste called tailings. These mountains of leftover rock are piled up into massive, unnatural hills. These piles are more than just an eyesore. They contain radioactive elements like radium, which decay slowly over thousands of years. This process constantly leaks an invisible, heavy gas called radon into the local air. This map shows how those tailings affect the environment. When rain washes over the piles, it picks up radioactive dust and toxic heavy metals, carrying them into nearby creeks and the community's drinking water. In this first stage, uranium is a slow, sprawling environmental poison, leaving behind a toxic legacy in the soil and water that can last for centuries. To move to the next step, that raw uranium is concentrated into a bright yellow powder. But a solid powder won't work for the next phase. Scientists turn it into a gas by attaching one uranium atom to 6 fluorine atoms. This creates a molecule called uranium hexafluoride, or UF6. This gas hides a chemical trap. If it touches any moisture, even ambient humidity, it triggers a violent chemical breakdown. If inhaled, the gas hits the moisture in the lungs and splits. Part of it turns into hydrofluoric acid, causing immediate internal burns. The rest becomes a soluble uranium salt that enters the bloodstream and travels to the kidneys, which can cause them to fail within days. During this chemical phase, the primary danger to a worker comes from acute chemical poisoning rather than the radiation itself. Next, the gas is pumped into centrifuges, massive spinning tubes. These spin so fast they can separate the slightly heavier uranium atoms from the lighter ones that are actually useful for power. Uranium atoms come in different weights, which scientists call isotopes. Enrichment filters the gas to collect enough of those rare, lighter atoms to create a reaction. If concentration hits 5%, you have a stable fuel that can safely provide electricity. But spinning past the 20% mark crosses a dangerous threshold, entering the territory of weapons-grade fuel. Achieving this level of purity in the real world requires massive, highly guarded facilities filled with endless rows of these precision machines. The final threat of uranium is a matter of physics. The same spinning process used for power is only a few steps away from building a world-ending weapon. The shapeshifter poses a triple threat: a metal poisoning the Earth, a gas burning the lungs, and a concentrated collection of lightweight atoms that can threaten global security. We continue to use this metal because its energy density is massive. A single pellet of nuclear fuel the size of your fingertip can produce as much electricity as nearly a ton of coal. Keeping this material contained requires a global effort. It takes constant environmental monitoring, specialized chemical suits, and teams of international inspectors to ensure everything stays safe. Uranium is a complex, multi-stage force of nature. Harvesting its benefits safely demands absolute precision, international cooperation, and a deep scientific respect.